Hi, this is going to be the first lecture on connectedness in topology. There have been a lot of requests asking me to produce videos on connectedness, connected spaces, etc. I know that a lot of students do not get how to work with connected spaces, etc. Okay, I have one small request. Since you had already asked for these videos, that means you had made an attempt to learn connectedness from a book or from your teacher or from some other course, etc. And you are not very comfortable, right? I'm just to take it as an assumption. Assuming that, okay, if you try to watch my videos, you will, okay, the way I approach connectedness is slightly different, even though I will prove they are equivalent, okay, there no doubt, okay. And the okay, so and you may try to kind of compare what you learned with what you are learning with from me today, so you'll get confused. For the time being, whatever you learned about connectedness, just set it aside. Think that you have not learned it. This is the first time you are going to learn. Okay, just go with me. You will see after a lecture or two, okay, you will know you had understood whatever you are supposed to learn from the earlier courses or your earlier attempts. Believe me, this will happen. Okay, so let us get started. Yeah, the sources, references I could give is there is an outline of a course in topology I had given, which is available from the usual MTTS website where you can download. And but then it's essentially with a lot more details in the context of metric space I have done, but you will see the proof do not use any metric spaces. Connectedness does not need the concept of metric spaces, and in the context of metric space there is no but characterization using metric, okay, which is useful. So what all we need is open sets, closed sets, etc. So okay, you can learn from that. So let us start with some examples. See, suppose I have R and some interval, okay, maybe open, closed, whatever, an interval, okay, or some kind of let's say open disk in R2, right? See these things, or you can even see a parabola, okay, parabola, or a circle, only circle now, right? Look at all these things, and whereas you compare this, okay, in R2 I have two parallel lines, right? Or in R I have only integers, subset of R, right? Or in R2 you think of two open disjoint open set. This is my set, okay. Or you can even look at the so-called rectangular hyperbola. Yeah, if you just watch these things, you will see a certain difference. In some sense, this whatever set you are considering, it is in a single piece. Do not worry much about what you mean by piece, etc. Okay, just try to first build intuition, then we will work through a concrete, precise definition. For example, look at this is one piece. Look at circle, this is one piece. Look at parabola, it's one circle. But if I look at hyperbola, it's not one piece, because there is this piece and this piece. This xy equal to 1 if you want. Yeah, or if I take two parallel lines, they are in two pieces. Or if I take common two disjoint open set, they are in two pieces. If I take Z, there are infinitely many pieces. Each is a piece. Okay. So there is a kind of distinction between the first class of objects and the second class of objects. The first class of objects have only one piece, whereas the second class of objects, okay, are maybe in more than one piece, 2, 3, and whatever. You understand this? So the first class of sets we would like to say connected, and second class of sets we would like to say not connected. This is what we want to have capture with a precise definition. Okay, so let us go to the definition. So this is my definition. Let X tau be a topological space. I say X is connected. This is my definition. If only if the only sets which are both only non-empty sets, let us say, so the only sets which are both open and closed are empty set and the whole space X. Do you see that in any topological space, empty set and the full space are both open and closed, and I'm going to say it's connected only, these are the only things, sets which are both open and closed. Have you understood this? That's it, very simple definition, right? Yeah, now let's try to understand it better. So what does it mean? Suppose I give a set U, okay, a subset of X, and I say this is not empty, but then this is open as well as closed. Okay, suppose my space X is connected, okay, and suppose I give an set which is both open and closed, it's non-empty set. What can you conclude? Remember, X is connected, that means the only sets which are both open and closed are empty set and X. I said U is not empty, therefore U must be X. Do you follow that? Yeah. Is the converse true? That is, if conversely, what is the converse? If U is non-empty, okay, if the only non-empty set, if the only non-empty open set in X is X itself, that means X is connected, right? What did it say? U is non-empty and open and closed, that means, okay, U must be X, that means U is connected. This is connected. Okay, since it's connected, this is the only set. Okay, so if U is connected, the only, if you say give me a set U which is non-empty, both open and closed, then it must be all of X. Okay, now converse, you give me you assure me the only non-empty open set, non-empty open and closed set. So let me just, I'm sorry, I didn't formulate it properly. Okay, let X be a space so that the only non-empty open and closed set it is X, that implies X is connected. Why? What does it say? It says that suppose to say U is connected, what should I do? Suppose U is a subset of X, okay, and U is open as well as closed, then I ought to say whether U is X. U is either empty or U is X, right? That's what it means to say X is connected. Do you follow that? Okay, right. Now what is given? You are given me as a set U. Suppose it's not empty. Suppose you are given me a set U which is both open and closed, and I have to prove U is empty or U is X. Suppose U is not empty, okay, then by hypothesis then U must be all of X. You understand? So I have proved this, so pause, review, proceed. So what have we shown? So I said X is connected. Let's look at the definition. If only if you give me U, okay, if U in X is open and both closed, that implies U must be empty or U must be all of X. So in other words, equivalently, if you give me a space X, it's connected if only if the only non-empty set which is both open and closed is or empty set and x. Non-empty set, therefore it's is x. The only non-empty set which is both open and closed is x. Do you understand this? Okay, let us, before you go further, you may recall when I talked about closed subsets, okay, then I proved in R, okay, the only sets which are both open with the usual topology, okay, usual topology, the only sets which are both open closed are empty set and R. So this means R is connected. This is the first example. Okay, we proved it. You see that? We already saw R seems to have one base, therefore it must be, intuitively we wanted to say it's connected. We have a definition, then we are using the definition, we have proved it. Okay, right. Yeah, okay. Now let's go to the general case. Suppose X is connected. Okay, not suppose X is not connected. What does that mean? That means there exists a subset A of X such that A is both open and closed, and A is not empty and A is not equal to X. Do you understand that? Because if A is connected, okay, if X is connected, the only sets which is both open and closed, they are empty set and X. You say it's not connected, that means there exists at least one set which is not empty set, which is not equal to X, but A is both open and closed. Do you understand this? Okay, pause, review, proceed. Make sure that you understand this. Okay, now what is that? Therefore suppose X is not connected. Okay, therefore there exists A such that A is not empty, A is not equal to X, but A is open and closed, right? Now let V equal to X complement A, X complement A, that is complement of A in X. What can I say about A? Can B be empty? If B is empty, that means X equal to A, that's ruled out. Can B be equal to X? B cannot be X. Why? Because B is equal to X, that means A is empty, but we assume A is not empty. You understand? So B is not empty, B is not, right? And since A is closed, A is open, this means B is closed, because B is complement of A. And since A is closed, this means its complement B is open. That means B is not empty, not X, and B is open and closed. Do you understand that? So if X is not connected, okay, what you have found is then there exists two sets, if you want, let me call U and V, such that what are the following things happen? 1, U union V is all of X, and 2, U intersection V is empty, yeah, and 3, okay, in fact if I assume one of them will follow, but let me not assume, then 4th is U and V are open and U and V are closed. Do you understand how many conditions I would write? If X is not connected, then what are the things? Okay, just because I can find A union B, what are the things I found? A is not empty, A is not equal to X, B is not empty, B is not equal to X, and both A and B are both open and closed, and A union B are disjoint, and A union B equal to X. All those 5 conditions I have written. Do you understand this? So many textbooks will start with a space being not connected using these conditions. Okay, Remember, you can always say certain things that I am not going to worry about. Okay, I am not saying all these five conditions. Okay, there are some overlapping, but let's not worry about. Have you understood? Pause, review, proceed. Conversely, okay, assume u and v satisfying 1 to 5 exist. Then I want to know x is not connected. Okay, yeah, how do I prove x is not connected? So see, u is not empty and it's not equal to x, right? That's by condition 3 by 3, right? And u is open and closed, right? Therefore this implies x is not connected according to our definition. When do I say a space is connected? If the only subsets which are both open and closed must be empty set or x. But you said u is both open and closed, but it's neither empty set nor x. You follow that? Yeah, right. Since these two are there, you know that, okay, if one of them, if you simply say they are non-empty sets, it will follow, but let's not worry about. Okay, pause, review, proceed. Okay, so these are the definitions, but let's not worry about. We are going to work with only 1, 2. Okay, if such a u and v, let me also give you a definition. If such u and v exists, then the pair uv is called a disconnection, a separation or a disconnection, or separation of x. But I will use the disconnection to be easier. But forget all these things. This is just to show you how my definition is equivalent to your standard definition which you find in many textbooks and from teachers. So let me recall quickly. I say x is connected if and only if the only sets which are both open and simultaneously closed are empty set and x. That's it. This is our definition. Keep this in mind. This is all you will need. Anything else will, you can see it's set theory and basic topology, it will follow. Okay, this tells you there is only one piece in some sense. You see that? Okay, right. Okay, please go through it. How does it say there is only one piece? Because otherwise, if there is a set u which is non-empty, which is not x, but which is both open and closed, its complement v will also have the same property. Therefore x is going to be 2 pieces u and v. That's the intuition you should have. Okay, now let's look at our standard examples. Okay, first suppose x with a discrete topology. Okay, is it connected? But the question, but remember here, if you take any set u, a subset of x, okay, it's both open and closed, because every set is open. Therefore every subset is open, its complement is also open, and hence u is both open and closed, right? So you may immediately conclude x is not connected, but then there is a caveat. Why? Can you see that? See, when I say this is not, I have to make sure, but if x has only one element, little x, okay, then the only topology on that is a discrete topology. Therefore this is connected. You understand that? Singleton set. But on the other hand, if number of elements in x is greater than or equal to 2, then x is not connected with a discrete topology. X with discrete topology. Why? If x has 2 elements, let us say, start with, okay, therefore x has and y both are there, and x is not equal to y. Therefore take u to be singleton x and b to be x minus x. Okay, then u is both open and closed. Okay, and u is not empty, and u is not equal to x. Why u is not equal to x? Because there is another element y which is not in u. You see that? Therefore I have produced a set which is not empty set, which is not the full set, but which is both open and closed. How am I able to do that? Because it's a discrete space, every set is both open and closed. So I only have to make sure if I take a singleton set, okay, it's not all of x, then I am through. Okay, pause, maybe proceed. The second example is x with indiscrete topology naturally. Okay, now in indiscrete topology, okay, the only sets are this. Okay, therefore the only closed sets are also empty set, and therefore by very definition this is connected, right? See, what are the open sets for indiscrete topology? Empty set. Is it closed? It's also closed. Okay, you understand that if I start with a subset of x, I want to be open. That means either a must be empty set or equal to x. That's enough. You follow that? Okay. Next, third, look at. Okay, what should I do? Yeah, right. Let's make an observation. Suppose I have a set x and a topology tau. Okay, let us assume it has the following property. Okay, any two non-empty open sets intersect now. Right, so I have u, and whatever open set you take, they will always intersect. Okay, like that. Any two non-empty open sets intersect. Then what can you say about x tau? X tau is connected. Can you see why? Suppose it's not connected. Suppose not. What does that mean? There exists a subset A, okay, which is not empty set, which is not x, and A is both open and closed. Right? Therefore, if I take B complement of A, then as I earlier explained, B is not empty, B is not equal to x, but it's also both open and closed. Yeah, right. Therefore A and B are non-empty open sets, and A intersection B is empty. But that's a contradiction, because what is our assumption? Any two non-empty open sets intersect. Therefore, okay, we conclude x tau is connected. As trivial applications, we will look at, okay, 3a and 3b. So let us start with this set n. Okay, with can you think of what topology I want? Cofinite topology. And start with R with the co-countable topology. Okay, let me call it TCF, TCC. Okay, now what do I know? In okay, these spaces have the same property, that is, if you take U and B non-empty open set, they always intersect. In any of these spaces, okay, they intersect always. Why? Suppose they don't intersect, suppose not, then what happens? U intersection V is empty. Therefore U complement union V complement is all of the space where x equal to n or x equal to r, right? Now in the case of n, I know this, since U is not empty, right? And it's, are you following? Yes or no? Right. Therefore what do I know about U complement? If U is not all of x, then you see, can U be all of x? If U cannot be all of x, because if U is all of x, then U intersection V will be V, and this is not empty, because by assumption V is not empty. Do you understand? Therefore I know U is not equal to x. Do you understand this logic? Right? So therefore U is an open set and U is not equal to x in the cofinite topology. That means in the case of n, U complement must be finite. Similar reason V complement must be finite. Therefore their union must be finite, but that's all of n. That's a contradiction. Yeah. In the same way, in the case of R, let's look at U complement union V complement. It will be all of R. Now what do I know? U, suppose U intersection V is empty, that means U cannot be equal to R, right? Therefore U is, and U is not equal to R. Since U is open in the co-countable topology, that means U complement must be countable. It cannot be empty set. Sorry, I have to say it's an empty set, right? Okay, anyway. Yeah. So yeah, you follow that? And U cannot be equal to empty set either. See, are you following me? Let me go back. I think I'm little not focused today. Suppose U intersection V is empty and U and V are in complement, right? Now yeah, and we assume U and V are non-empty sets. Okay, therefore I claim U cannot be equal to R. Suppose U equal to R, then U intersection V will be V and V is not empty, right? So this contradiction shows U is not equal to R. Do you understand? Yeah, this is the logic which I gave. Yeah, I was correct. There was no mistake. Okay, right. Therefore U is not equal to R. For similar reason, V is also not equal to R. Now U and V are complement. Therefore U complement must be a countable set, and similarly V must be countable set. Therefore U complement union V complement, which is equal to R, must be countable. That's a contradiction. Yeah. So this contradiction shows that n with cofinite topology and R with co-countable topology are connected. Is it okay? So why they are connected? It follows for a single observation. What is the observation? If I take a space in which any two non-empty sets always intersect, that space has to be connected. That's an observation, which is very trivial observation. Yeah, please go through the proof again, pause, review, proceed. Now let's look at the next example. R with VIP topology. As usual, VIP is 0. Now notice that you give me any two open sets U and V, so they are non-empty, right? Then if they are non-empty, remember, since U belong to VIP topology and V belong to VIP topology, P always in U, P is always in V, therefore U intersection V is not empty. Therefore what is the conclusion? R with VIP topology is connected. Yeah. What is the next example? So next example is R with outcast topology, and as usual 0 is the outcast. Right, now what are the open sets here? Okay, if U is not empty, then U belong to outcast. That means what? 0 is not in U. Yeah, right, good. Now let's look at the 0. The only open set which contains 0, the outcast, is R itself. Right, you understand? I claim because of this is connected. How many of you can see this? Okay, suppose it's not connected. Okay, that means there is an open set U which is not empty, which is not equal to R. Right, okay, which is both, U is both open and closed. Then therefore its complement is also both open and closed. Now take 0 is in R, which is equal to U union V. Therefore 0 must be in U or 0 must be in V. You follow that? 0 is in U or 0 is in V. But I have a contradiction. The only open set which contains 0 is, that means U is equal to R, or in this case V equal to R, but our assumption is U is neither empty set nor R, and similarly V is neither empty set nor R. This contradiction shows this is connected. Yeah. Now let's look at the next example. Is it 6 or? Yeah. Now let's look at R with a lower limit topology. Right, you may recall, if you have gone through my lectures on closed sets, I have proved any set of this form, this is a basic open set which is also closed. Right, this is also basic open set, this is open. Therefore R towel is not connected. How did I prove it's closed? Because the complement is this and this. Okay, that is open. Okay, that's how we prove this is both open and closed. Therefore R with lower limit topology is not connected. So let's look at the last example. Okay, R2 with the dictionary order topology. I claim, okay, there also we already seen any vertical line. Let's look at LC to be the vertical line C comma Y, where Y is an R. Okay, this is your LC, this is the point C. Now this is open because we have seen, okay, the basic open sets are like this. We have seen these things, right? So therefore with respect to this, these are open. Okay, but on the other hand, what is LC complement? That is union of LD, where D is not equal to C, all other lines. Right, therefore these LDs, these are also open, arbitrary union of open sets, therefore this is open. Yeah, therefore what I have found is LC is both open and closed, and it's not empty, and it's not equal to X, R2. Therefore R2 with the dictionary order topology is not connected. Yeah, very good. Now let's look at one more example in R. See, I define only connectedness of a space, right? Suppose I was subset A of X, X tau is a topological space. Okay, when do I say A is connected? Okay, that is if only if A tau A is connected, where tau A is the subspace topology. Okay, and this is the one which really gives a lot of problem to students, because many textbooks will try to write down a disconnection. If a subset A is not connected, then they will try to show what kind of disconnection you should have. Okay, for X I had a disconnection, do you remember? If U is a non-empty proper open set which is also closed, then its complement B, then U union B equal to X, etc., etc., and the pair U is called a disconnection. So here also you can do, but then you will try to write down a lot of conditions, so that confuses a lot of students. So let's not worry about. You will see we don't have to learn that definition at all. Remember this: A is connected if only look at the subspace topology on A, and the space A tau must be connected. Are you happy? Keep that. We will see a much more efficient way of looking at these connected spaces in the next lecture. Okay, keep this in mind. Let me go through. Okay, now let's look at R. Okay, with this. Okay, let us say yeah, the union R minus singleton 0, usually calls R star, the set of non-zero reals. This is a subset of R. Is this connected? So what are the subspace topology? Now you see that. Now let's look at, are you following this? So I have R, and this point is removed, this is 0, this is removed. Okay, now you can see R minus 0 is union of minus infinity to 0 and union of 0 to infinity. You understand that? And these are each one of them is a subset of R star. Yes, and is this open? This is not empty. This is also not empty. I don't need that. This is let's look at only one. Let's look at only 0 infinity. Okay, this is an R star. Is this open in a subspace topology? Yes, because this is open in R, 0 infinity, open in R. Therefore its intersection with R star is open in R star. Open in subspace topology. Yeah, right. And it's not empty, and it's not equal to R star, right? Is it closed in R star? Yes, because its complement is minus infinity to 0. The way we argued, this is open in R star. The same way we argued 0 infinity open, this is also open in R, and hence its intersection R star is itself, therefore it's open in R star. Since the complement is open, okay, 0 infinity is also closed. Therefore I have shown 0 infinity is both open and closed, and 0 infinity is not empty and it's not equal to R in R star. Therefore R star is not connected. Now do you see that our intuition again comes? What was our intuition? Okay, R star has two pieces, right? What are the two pieces? Minus infinity to 0 and 0 to infinity. Therefore I should expect it's not connected, and we have proved it rigorously. Yeah, please go through all these examples, and if I know there are disconnection etc confuses you, forget it for the time being. Okay, that's the way you might have learned. It will confuse you. You stick to my definition. When I say R, okay, I'll stop sharing. I'll come to that. Yeah, so I will stop the lecture here. Please go through this and do not worry about the disconnection. You simply remember my definition. When I want to say X is connected, that means the only sets which are both open and closed must be empty set and the full space. So if it's not connected, what does it mean? That means there exists a non-empty set which is also a proper set, because it should not be empty set, it should not be all of X. So it should be non-empty, it should be proper set. And with what property? It should be both open and closed. That's it. You remember these two? That's it. If you get the first one, you get the second one. From the second one, you can get the third one. Third one is the so-called disconnection criterion. What does it say? If I have a set U which is not empty, which is not all of X, but both open and closed, its complement B is not empty set, and it's not X, and it's also both open and closed. Therefore I can write X as union V. That's it. Now with these things, please go through the example once again. You will appreciate. In the next lecture we will talk about what are all the connected subsets of R, and a powerful criterion, okay, which will work with connectedness and connected sets, also connected subsets, that will make our life much easier. Okay, I'll stop here. Take care, stay safe.